Alright guys, in this video we're going to kind of shift gears away from polar coordinates and I'm going to talk about vectors. I'm actually just going to hit you with a bunch of different concepts dealing with vectors, and so there's a lot of stuff here. Each thing individually is not overly challenging, but I want to make sure that we talk about a lot of different ways that we can look at vectors and use vectors. So first of all, the definition is that a vector has both magnitude and direction. Okay, so it's going to tell you, it would tell you the length, or the like we could use this for force, we could use this for a speed. That's the how much, right? So magnitude is how much of something, and then direction involves at what angle. Okay, so where is this force being applied? Where is this speed being taken? So the one thing that you guys are probably used to with vectors that you really haven't thought about is velocity. So whenever you talk about velocity and how that differs from speed, velocity is how fast something is going and in what direction, whereas speed is just how fast. So speed would be what is considered a scalar quantity, and the scalar quantity is simply just magnitude, so how much, and there's no direction with that. Okay? First thing I want to get into is how we add vectors, and then how we take a vector and multiply by a scalar. So I'm going to start with these two vectors, and we will call them vector v and vector u. And notice every time that I have this black vector v, it's the exact same length in the exact same direction. And then every time I have this orange vector u, it is always the same length and in the same direction. So there are a couple different ways that we can show addition of vectors. If I take vector v and I start with that, and then at the end of vector v, I simply just put vector u, then the vector v plus u is the vector that goes from the start of v to the end of u. And that would be that blue vector, v plus u. Another way that I can do this is I can put the base of each vector together. So again, this is vector v, and this is vector u. And I just base them from the same spot. And then what I do is kind of what's called completing a parallelogram, right? So this is also vector v up here, and this is also vector u right here. And where those two would end, that would be the end of this vector v plus u. So there's a couple different ways to look at adding them. You can just stack them, or you can base them from the same spot and complete a parallelogram. Notice this blue vector both times is exactly the same, and that should happen. Vector v plus u should be in the same direction and the same length both cases. Okay, multiplication by a scalar. Let's start with vector u. If you multiply by any kind of number at all, that just doubles, or it multiplies the magnitude, right? So this would be the vector 2u. So that would be essentially twice the length of vector u, and in the exact same direction. This one's much smaller. This would be a vector that would be a fraction of u, like 1/2 u. And then notice this last one is going the exact opposite direction. Okay, it's about the same length, should be the same length as vector u, but it's the exact opposite direction, so that means that is the vector negative u. So a negative multiplication will just take that magnitude and, take the magnitude, keep it the same, and take the direction and make it go the exact opposite. Okay, this is a part where people always get confused. So we are going to write vectors in what is called component form, and that is what you see right here. So the vector v can be written as a comma b, and notice these are not parentheses. Okay, they're kind of like arrows almost, arrow tips. But a is simply the horizontal component of vector v, and b is the vertical component of vector v. And I did put a note here. This is not the exact same thing as the coordinate point a comma b. So here's what I mean by that. Let's say I had the coordinate point 3, 4. Okay, so 3, 4, I would go right 3 and I would go up 4, and that's the coordinate point 3, 4. Now the vector 3, 4 is simply just a vector where its horizontal component is 3 and its vertical component is 4. But that does not have to be centered at the origin. It does not have to start from the origin. Now, if it did start from the origin, then if I did a horizontal component of 3 and a vertical component of 4, I would end up with a vector that would point to and end up in the same exact location as the point 3, 4. However, I could start this vector anywhere I want to, and I could just make sure it has a horizontal component of 3 and a vertical component of 4, and I could graph that vector over here. So the vector v could be written here, it could be written here. I could draw this vector anywhere that I want to, and just notice that like we had up here, every single time that I'm going to graph this vector v, it is going to be in the same exact direction with the same exact magnitude, but it could move around. It does not have to be centered or starting at the exact same location. Okay. Oftentimes it is easy to start it from 0, 0 because then it does end up at the coordinate point a comma b, but it does not have to. The component form of a vector, again, is how we're going to write that. How we can come up with that, if I know where a vector starts and where it ends. So in this case, I've got a vector u. It is starting at the point -2, 5, and it is ending at the point 3, 7. The question is, what is the component form of this vector? And the way that we figure that out is we just figure out how far horizontally the vector traveled and how far vertically. So horizontally, it ended at a point of 3 horizontally, and it started at a point of -2. So if I subtract 3 minus -2, that gives me a horizontal, this would be A, this gives me a horizontal component of 5. The vertical component B, it ends at a coordinate point of 7, a y coordinate of 7. It started at a y coordinate of 5, so it traveled vertically a distance of 2, and therefore the component form of vector u is 5, 2. If you don't believe that, I would just encourage you to, on a graph, plot these 2 points, and then figure out how far you go horizontally, how far you go vertically, and that should be 5 and 2. The next one is, I know the component form of the vector, and I know the starting point. Question is, what is the end point, or the terminal point? Where does it stop? So if we know that it starts at 2, 4, and then it travels horizontally at a distance of 3, I know that the coordinate point that it's going to end up with at an x coordinate is 5. And same thing, if we start with a coordinate of 7, and if we start with a y coordinate of 4, and then we travel horizontally a distance of 7, then that y coordinate is going to be 11. So again, starting at 2, 4, ending at 5, 11, that vector's component form would be 3, 7. The magnitude of a vector is simply just, again, how long that vector is. And if we think about taking a vector and breaking it down into a horizontal component and a vertical component, that would be like A and B in this case. If I think about breaking that vector down into strictly horizontal and vertical components, then to find the length of this vector, I simply just need to do the Pythagorean theorem. And that's what this is showing. So the notation for magnitude is looks like absolute value here. But the operation that we're going to do is essentially like finding the hypotenuse of a right triangle. So if I want to figure out, I have a vector here with horizontal component 2 and vertical component -3, and I want to find the magnitude of that vector, I'm going to do the square root of 2 squared plus -3 squared. So that's going to give me the square root of 4 plus 9, which would be the square root of 13. Okay, again, that tells me the exact length of that vector. The magnitude of vector v, I would have the square root of 5 squared plus 0 squared, which would be the square root of 25, which would be 5. Okay, if I have more than one vector and I want to do some operations with them. So what you see here is adding those vectors, subtracting those vectors, or taking the vector and multiplying by some constant. All this is saying is you add the horizontal components, add the vertical components, or subtract them, or multiply each one by the constant. Those operations, I think, are pretty self-explanatory in what you would, I think, intuitively think that you would do. So I'm going to run through these, and then I'm probably going to end this video and pick up with the rest of this on a separate video. So I have vector u, which is 2, negative 3, and vector v, which is negative 1, 2. And I want to find the following. So u plus v, that means I'm simply going to add the horizontal components. So 2 plus negative 1 would be 1. And add the vertical components, negative 3 plus 2 would be negative 1. U minus v, so I'm going to subtract the horizontal components. 2 minus negative 1 would be 3. And the vertical components, negative 3 minus 2 would be negative 5. The vector 2u, I'm just going to take the vector u and multiply both of the components by 2. So that would give me 4, negative 6. Negative 3v, again I'm just going to take vector v and multiply each component by negative 3, which would give us 3, negative 6. And the last one, this is actually what you call a linear combination of two vectors. So I'm going to do twice vector u and then add to that 3v. It may help in this case to do these things separately and then add them together. What I mean by that is figure out what 2u is, which we already have is 4, negative 6. Figure out what 3v is, which would be negative 3, 6. And then take those two things and add them together. So 2u plus 3v would be 4 plus negative 3, which is 1, and negative 6 plus 6, which is 0. And that would be my linear combination, 2u plus 3v.